Section 3.5, graphing functions using reflections about the axes. Another transformation that can be applied to a function is a reflection over the x-axis or the y-axis. A vertical reflection, this reflection right here, let's say we have this graph right here. A vertical reflection reflects a graph vertically across the x-axis, while a horizontal reflection of the same graph reflects the graph horizontally across the y-axis. So a vertical reflection reflects about the x-axis, a horizontal reflection reflects about the y-axis. Notice that the vertical reflection produces a new graph that is a mirror image of the original graph about the x-axis. The horizontal reflection produces a new graph that is a mirror image of the original graph about the y-axis. Here are the mathematical application or the mathematical way of saying that a graph is reflected vertically or horizontally. If you are given a function f of x, a new function g of x equals negative f of x, this is a vertical reflection of the function f of x, also sometimes called a reflection about or over the x-axis. How do we know that? Because of that negative sign right here. We know that each output or each y from positive becomes negative, and if it's negative becomes positive. So all of the values for y that are positive, they're going to reflect and be negative, and anything that was negative is going to be positive. If you are given a function f of x and your function g of x is a horizontal reflection, if g of x is equal to f of negative x, so this is a horizontal reflection of the function f of x. Sometimes we call that a reflection about the y-axis or over the y-axis. So here is an example of how we're going to apply a horizontal reflection or a vertical reflection. We're going to work with the function f of x equals to the square root of x, which is the parent function. It's going to look something like this. Roughly, okay, here is the square root function. It's the original one. A horizontal reflection is going to reflect the graph about the y-axis. So the new function or the new graph, it's going to look like a mirror of the original graph reflected about the y-axis, and that is basically a horizontal reflection or reflection about or over the y-axis. The vertical reflection is going to happen across the x-axis or over the x-axis, and the new graph is going to look like a reflected image of the original graph over the x-axis or about the x-axis. So that is going to be the new function or the new graph of that function. So if I would like to rewrite the equation again, the new transformed equation for this one is g of x equals the square root of negative x. And for the other one is going to be g of x equals to negative square root of x. That is basically the reflection. Determine even and odd functions. Some functions exhibit symmetry so that reflections result in the original graph. For example, horizontally reflecting the toolkit function f of x is equal to x squared, or f of x is equal to the absolute value function will result in the original graph. We say that these types of graphs are symmetric about the y-axis. A function whose graph is symmetric about the y-axis is called an even function. If the graph of f of x equals x cubed and the graph of f of x equals 1 over x were reflected over both axes, the results would be the original graph. See the pictures below. We say these graphs are symmetric about the origin, which is also called an odd function. This is called an odd function when the graph of the function is symmetric about the origin. So as you can see, here is the parent function, and then reflecting it across the y-axis, it's going to look like that, or reflecting it horizontally. And then if you reflect it about the x-axis, it's going to return back to the original shape. So after two transformations, reflection about the y-axis and then reflection about the x-axis, the function returns to the original shape, and this is called an odd function. Note that a function can be neither even nor odd if it doesn't exhibit either symmetry. For example, f of x is equal to 2 to the x is neither even nor odd. Also, the only function that is both even and odd is the constant 0. So f of x is equal to 0 is the only function that is both even and odd. Even and odd function mathematically. To test this, if a function is even, you're going to replace each x with negative x. If the function f of x is equivalent to the function f of negative x, then it is even. That is how you're going to find out algebraically. So you're going to substitute each x with negative x, and then if the resultant function is similar or it is the same as the original function, then we say that this function is even, and it is symmetric about the y-axis, and we know that because it's even. If you replace each x with negative x and the resultant function is the same as negative f of x, then we say the function is odd or it is symmetric about the origin. If the function does not satisfy either rule, it is neither even nor odd. So here are some examples. So the first function here, represented with the first graph right here. And the second one is represented with this graph right here. And the third one is represented with this graph right here. Notice how all of the graphs are symmetric about the y-axis, the ones that I highlighted here. And notice how the exponent of each of these terms is even, including the constant, because there is an x to the 0 power. So here is an even power, even power, even power, even power, even power, and there is an invisible even power here, even power, and there is an invisible even power. So each term of these has an even power, which will lead me to the observation of I can actually tell if a function is even if each of the powers of the terms is even. Then that is going to be an even function, like in the highlighted examples here. Now, in the second set of examples, the first function here is represented with this function, and the second function is represented with this graph right here. You notice that the first graph is symmetrical about the origin, because if you reflect it across the x-axis and then the y-axis, or the y-axis and the x-axis, you're going to obtain the same original graph. Same with the second graph right here. It is symmetric about the origin, because if you reflect the graph horizontally and then vertically, you're going to obtain the original graph. Now notice what we have here as a power. The power is odd, the power is odd, which is 1. Odd, odd, and odd, which is 1. So when all of the powers are odd, or every term in the function has a power that is odd, the graph of the function is going to be odd, or the function is going to be odd or symmetrical about the origin. So you can tell just by looking at the powers here, a little bit of observation, we came up with this rule. If you have a mixed powers, so let's say you have the function f of x equals to 2x squared minus x plus 1. Notice how you have even here, odd here, even here. So you're going to say this is neither. It's neither even nor odd, because if you graph it, you're not going to see or notice that it is symmetrical about the y-axis. You're not going to be able to see either that it's symmetrical about the origin either. And because of the mixed powers here, we are sure that this is neither even nor odd.